One way that we can figure out what will happen in a situation in optics is to use Huygens principle. If we want to understand this, we need the concept of a wavefront. So let's imagine we have a point source of light sending out light in all directions. This is a little bit like a rock dropping in a pond, only in 3D. If we connect all the points where the waves reach maximum electric field first, for example, it would look like this picture. So you've got a maximum there and there and there and there. And of course, there's a bunch of directions we haven't drawn. But all of those should be exactly 1/2 or 1/4 wavelength away from the source, the way this is drawn. So that shape will be a sphere. That sphere is the wavefront. We could similarly draw this and say, how about the second maximum, or the third, or the fourth, whatever we want to do, whatever point we identify, it'll be at the same place on each of these waves in each of these directions, so we get spherical wave fronts from this. The wave front is just a surface of constant phase or constant position along the wave. If we rearranged it and instead we say we've got a flashlight going left to right across the page, we can again look at something that lines up all the points of constant phase, for example, this red dotted line, or the green dotted line, or the blue dotted line. These are all wave fronts, and what we get is if we have parallel light coming left to right, we'll have parallel wave fronts up and down the page. Huygens principle says we can figure out what will happen to light in a given situation if we consider every point on the wavefront to act like a spherical radiator, just like this thing. Now, of course, if we're in 2D, like we are on this screen, it's really going to look like a circular radiator. Instead of producing expanding spheres, it'll produce expanding circles. If we imagine every part of this red dotted line as emitting this expanding circle, and at one instant we connect a line tangent to all the circles, we get the green dotted line. This is the next wavefront. We can explain refraction the same way we explained it before, by this difference in speeds. If we imagine all these circles expanding from this wavefront before it gets to the water, or whatever this medium 2 is, we'll get these parallel lines, these wavefronts. These were like the axles of the wheelchair that we talked about. But then when we get here, because the speed of light inside medium 2 is lower, that means the distance it goes in a certain time is lower. So here we have v2t for the radius of a circle, and back out here we're still at v1t. When we connect all those wavefronts, now we get something bent here, like this. The wavefronts bend as they hit the change in medium, and that gives us a new direction, this theta 2. We'll use this more when we look at diffraction, which will be a couple of chapters away from us. We know that the electric field has to oscillate perpendicular to the direction that the light travels. If you think about that, that gives us an infinite number of possible directions for that. For example, if light is coming out of the screen at us, all of these different colored lines, all these different directions are possible directions of polarization, directions of E-field alignment. If we want to look at this and see what a particular light wave, what its polarization is, we use something called a polarizer. This is for visible light made of a sheet of plastic with long chain polymers. This is usually called Polaroid film or a Polaroid filter. And while it's light with its electric field along the direction of those molecules that gets absorbed, and light with its electric field perpendicular to the chains that gets transmitted, we'll usually draw it. We'll draw lines in the polarizer to indicate which way the polarization will be passed rather than blocked. The thing about this is a little bit weirder than you would expect. And this will come back when we talk about quantum mechanics if we get that far. That is, the light doesn't have to be polarized exactly in the right plane to get through a polarizer. If we hold the polarizer so that its lines of transmittance are up and down, that doesn't mean the light electric field has to be up and down exactly. There's a chance for light with an electric field in any direction except exactly perpendicular to these lines to go through. A lot of times the analogy we use is this beaded curtain thing that you can buy online. If you imagine you're trying to walk through that and you're carrying something like a meter stick or a pipe or something, it would be very easy for you to get through if the meter stick is aligned vertically like these strings of beads. On the other hand, if you turn the meter stick perpendicular to the strings, it's going to be very hard for you to get in without moving all of the beads. As we look at this, as the angle of the stick changes from vertical to horizontal, the chance of getting through drops. If you think about this, what we're really talking about is a projection, just like you saw when you looked at vectors in the beginning of the first semester. If we want the projection of the stick, which is the electric field, in the direction of the curtain, which is the polarizer, all we would need to use is the cosine of the angle between them. That's from ordinary vector math. We need a little bit more than just the cosine, though, because the intensity of light, we've already figured out, depends on the square of the electric field vector. So if we combine these two things together, we get the law that governs polarization, and that tells us that the I that's transmitted is equal to the I that's incident times the square of the cosine of the angle between the two. This means if we have vertically polarized light and send it through a polarizer that's also vertically oriented, the angle between the two would be 0, cosine theta is 1, and it would predict we get exactly as much light back out as we sent in. Of course, it doesn't work exactly like this in real life because nothing is perfect. Just like a very expensive, very clean window is not invisible. You can still see it's there because it reflects a little bit of light even though it's supposed to be transmitting at all. The same idea with the polarizers. We're going to pretend we have ideal ones when we do homework problems and test problems, though. The way these problems would look on a test, something like this, if we wanted to draw incoming light, this would indicate that it's polarized in the up and down direction. These lines here in this polarizer and this 0-degree angle, that would indicate it's in the same direction, and then our outgoing light wave would also be in that direction. As a different example, if the incoming light is vertically polarized and the polarizer is oriented at an angle 75 degrees to the vertical, what we would get is outgoing intensity is cosine squared of 75 times incoming intensity, or about 0.067 times the incoming intensity, or we could also say about 6.7% of the light is transmitted. Notice that whatever light does get through here, it is now completely in this direction. It's in the exact same direction as the polarizer when it gets through. The light that we generally see, sunlight and light from overhead lights, indoor light fixtures, is unpolarized, and what that really means is random mix of all polarizations. If all polarizations are present, what actually happens if you do the math is you see that 50% of the intensity gets through. So this is what I usually draw when I'm talking about unpolarized light. I show several polarizations here. When it goes through this polarizer, whatever theta is, you get half the intensity coming out. And of course, what comes out will be aligned with this polarizer. What if we try this problem? Let's say we have unpolarized light. We go through a polarizer at this angle and then a polarizer at this angle. We know that starting with unpolarized light, we get half of it through the first polarizer, and what comes through will be oriented at an angle of 30 degrees to the vertical. How much of it gets through this next polarizer? What we need to know is not the difference between 30 degrees and 40 degrees, but notice they're measured from different directions, and I'll typically do that on a test. It's not really to confuse you, but it is to make sure you know what's going on. If we look at the angle between these two things, if this is 30 degrees to the right of vertical, this is 40 degrees above horizontal. I could say that's 50 degrees to the left of vertical. So if we have 50 degrees to the left and 30 degrees to the right, that's a net 80-degree angle between them. So if I want to know how much comes out on this side, I take the 50% that I get through the first one and multiply it by the cosine squared of 80, and I get about 1.5%. There's another example that tends to surprise people if you think of these polarizers as being like fences. If we have two crossed polarizers, I'll get half of the unpolarized light through the first one, but 0% of the light through the second one, because now it's been arranged to be horizontal and the second polarizer is vertical. We know the cosine of 90 is 0, so that blocks it completely. If these two fences block all of the light, what about if we put a third fence in between them, oriented at 45 degrees to both of them? What we'll see there is, again, we get half through the first one. Then going through the second polarizer, we notice our angle between the incident light and the polarizer is now 45 degrees. Cosine squared of 45 is 1/2. That means we get half through the first one, half of that through the second one, and then through the final one. Now our light is at this 45 degree angle. We go through a vertical polarizer, so we get another factor of cosine squared 45, and that gives us another factor of 1/2, so that means 12.5% of the light gets through. So in other words, we had a perfect fence with these two polarizers. We add one in the middle, and now 1/8 of the light is able to make it through. That's a little bit different than what we would expect for just regular mechanical fences. There's one other interesting effect that we see when we talk about polarization, and that's polarization by reflection. Let's say we have an unpolarized beam coming in from the left. So I've got arrows in all directions here, in the plane, out of the plane. The only restriction is they have to be perpendicular to this direction that the light is traveling. We can break that down into two perpendicular directions. We can say the red line, and then this green circle and dot can represent what's going into and out of the plane. These two together can represent all the polarizations, because any polarization you can think of can be written as a linear combination of the two. So it comes down here. We know that the outgoing light will go at the same angle as the incoming light. The incident angle and reflected angle are the same. Depending on the relative values of the index of refraction above and below the gap here, we can find what this angle of refraction will be. But if you look at what would happen, let's imagine the green circle and the red arrow travel along here, and then they hit this point. Both of them can go on down into the water or glass or whatever this is just fine. They're still perpendicular to the direction of travel of the light. But notice what would happen if we tried to translate this to the reflected beam. The green part is fine, but this red polarization would be directed along the light's direction of travel, and that's not allowed. So what happens physically is that portion of the light gets removed, light that's polarized that way. This polarization by reflection can be seen in a bunch of different places. One of them is the effect of light hitting water or glass on a windshield, something like that. This is where glare comes from. We could make dark glasses just by using a filter and blocking a certain fraction of the light without paying attention to where it came from. But if instead we use polarizers that are oriented to not pass this light, that means that in addition to blocking 50% of all light, we'll block 100% of this glare. The angle where this happens completely rather than just partially is called Brewster's angle. We could do a little bit of math and see that what we really need is a 90-degree angle between our refracted and reflected rays. That's what'll cause this. If we do the math, we see tangent of Brewster's angle must be n2 over n1, where these are our two indices of refraction. If you want to see what this looks like in practice, you can get a polarizer. They're relatively cheap. The fancy ones for cameras are not particularly cheap, but you can see here on the left side without the polarizer, you just see reflections in the water, trees or whatever. On the right side, you get rid of the glare, you can see into the water and see the fish. Now this is a simulated image, but this is what it really looks like. It's a good simulation. You can see the same thing on windshields. This is from a site that has something to do with filmmaking. If you look, there's a lot of glare on the windshield of this car. You put the polarizer in place and now you can see through there without any problems.